Hello, everybody. So then in this particular video or sequence of videos, we're going to talk about eigenvalues, eigenvectors, and one of the main uses of them, which is called similarity. Now, there's a very obvious connection between similarity and a certain property about linear transformations, but I won't talk about that at all today. That'll be for the future. So to get you started, what do we mean by similar matrices? So we're going to say that two matrices, A and B, that are both n by n, are similar if there's an invertible matrix P, so that P inverse times A times P equals B. I know that looks awful. Your first thought is, why would you do that? There's a very good reason, and it's because of linear transformations, which we won't talk about for a little bit, because you need to know how to understand the concept of similarity and how to determine if two things are similar or not first, before we launch into the idea as it comes through by looking at linear transformations. So there's a few things here you should notice. If A is similar to B, that algebraic equation is true by definition, but it's actually easier to write it instead by just pre-multiplying both sides by P to get A times P is equal to P times B. So it's almost like that the matrix P helps commute the product to turn A times P into P times B. It'd be nice if it was P times A, but it's not. So then it's kind of a way to get around the idea of commutativity not being true for matrices. Also, though, that if you have A and B, certainly P depends upon them. Once you give me A and B, P depends upon those things. But P is not unique. For a given choice of matrix A and matrix B, there could be lots of matrices P that demonstrates or verifies the similarity equation. For example, if A and B are both the identity matrix, well, then P could be anything, because A times P would just be P, and B and P times B would also just be P. So then you'd automatically have that P could be any matrix you like, as long as it's invertible. Now, the point on one level of similarity is that it sets up a kind of equality. When you think of equality has three main properties. A equals itself. If A equals B, and that means then B equals A. And then the last one, if A equals B and B equals C, then A equals C. It just so happens that the property of similarity is what we call an equivalence relation. It's a kind of equality between matrices. Now, before I go explain why these are all true, you should get an idea what it means. So if you take the set of all n by n matrices, and there's obviously an infinite number, similarity will take that set of all possible n by n matrices and partition it into sections so that all the matrices in this one group are similar to each other, and all the matrices in this group are similar to each other. And in those two groups, no matrix from this side is similar to any matrix on that side. It's like you take an overall, like a big, gigantic cookie pan, and you're just cutting up the cookie pan into different sections. So similarity is a way to chop up the set of all possible n by n matrices into matrices that are similar to each other. Now, why that's true, that involves a different class, but you get the idea. I need to explain why these things are true. So I'm only going to do one of them. The rest can be seen in homework, or if you read the book, you could find your own proofs. They're not really difficult. So I'll do, let's say, just the second one. Let's suppose that A is similar to B. Then that means there is an invertible P, so that P inverse times A times P is equal to B. All right, so then what I want you to do is I want you to pre-multiply both sides of that equation by P. That would give you A times P equals P times B. In other words, multiply the first equation on the left by P. But then in the second equation, I want you to multiply on the right by P inverse. That will then give you that A is equal to P times B times P inverse. Now we're going to be sneaky. Remember that P is invertible. So then this is the same as saying A is equal to P inverse times B times P inverse. So notice that I'm able to find an invertible matrix. So if I take B and I pre-multiply that B by the inverse of that matrix, and then multiply post by that matrix, you get A. That's the very definition of what it means for B to be similar to A. And that's the basic idea. It's just a matter of just using some tricks we know about algebra and matrix multiplication. Okay, the others I'll just let you try on your own, or maybe in your homework. There are some properties. Now, if we think that similarity is a way of saying that in some way matrices are equal to each other, you might want to know that if matrices are similar, so in other words, some way equal, are they also equal in other ways? And the answer is, yeah, actually everything practically, like lots of things. So one is, if that two matrices are similar, then their determinants have got to be the same. That also therefore means that if one is invertible, then the other is invertible. So if A is invertible, then B is automatically invertible, and vice versa. Why that's true is incredibly easy. As a quickie proof, not meant to be difficult at all. So then if A is similar to B, then P inverse times A times P is equal to B for some invertible P. But then just take determinants. So the determinant of B would then equal to the determinant of P inverse times A times P. But one of the properties about determinants is it can distribute through matrix multiplication. So that's then the determinant of P inverse times the determinant of A times the determinant of P. But we know how to find the determinant of P inverse. It's just 1 over the determinant of P. Then you have times the determinant of A and times the determinant of P. Also, since we know that P is invertible, the determinant of P is not 0. That means that these cancel, giving you the determinant of A, and that's it. So then if two matrices are similar, then their determinants must be equal. Now I'll do one more. It just so happens that if two matrices are equal, then they have to have the same characteristic polynomial. And if they have the same characteristic polynomial, of course, then they have the same eigenvalues and the same multiplicities. And they actually have more too. But proving this is also pretty easy. It's just a matter of doing clever things with determinants. So I'll show you how. So then as a quick proof, once again, I'll do the same thing I just did before. Let's say that since A is similar to B, then it means that P inverse times A times P is equal to B, and that's for some invertible B. Okay, I want to know what is the characteristic polynomial for B. By definition, that is, it's just the determinant of, you remember, it winds up being, that's P minus lambda times I. But that's the same as writing this. That's the determinant. B is P inverse times A times P minus I lambda times I. But I can be written as P inverse times P. But then that's the same as writing the determinant of P inverse times A minus lambda I times P. Just do the multiplication all the way through, you'll see it's the same. But then that's the same as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. And as I argued before, since P is invertible, the determinant of P is not 0, and these are inverses. So they cancel, giving you the determinant of A minus lambda I, and that is the characteristic polynomial for the matrix A. So yeah, if two matrices are similar to each other, they have the same characteristic polynomial. So if they're equal in one way, they're equal in this other way also. There's a lot of these things. So there's so many. I'm just going to write down the ones that we might need recently or in the near future. There's many more beyond this. So suppose you have two matrices that are just similar to each other. Then this must be true. First off, their determinants are equal. You just saw that. If their determinants are equal, then obviously they're both, if one's invertible, then the other must be invertible because their determinants are either both not zero or they both zero. Also, we know they have the same rank. Now that's harder to show, but it involves a video that you just saw with the rank of a product being equal to the rank of one or both of the factors, assuming one of the matrices is going to be invertible. It's incredibly easy to prove. I'll let you look at it yourself. So they have to have the same rank. They all have to have the same characteristic polynomial. We already know that. I just proved that to you. If it has the same characteristic polynomial, it's got to have the same eigenvalues, and it has the same it has to have for every eigenvalue the same algebraic multiplicity, and they actually have to have the same geometric multiplicity too. That's not in your book, but it's actually true. They have to have the same eigenvalues, and each eigenvalue has to have the same algebraic and geometric multiplicity for the matrix A and matrix B. Also, that if two matrices are similar, then their powers are also similar. That's super useful. This is actually one of the reasons we even do or discuss similarity, is that little algebraic fact. Now that's only true for positive integers. That's the reason it's only true for positive integers, is because we can't use negative integers unless the matrix A is invertible. But if the matrix is invertible, then B is invertible, and then A to the n is similar to B to the n, actually for all integers, either positive or negative. So that's really neat. I won't prove all of these, but they're nice things to know. But you have to pay attention to the order of this theorem. It says if they're similar, these are all true. It does not say if these are all true, the matrices are similar. And in fact, you can find really simple examples of matrices that have the first 6 properties, and yet the matrices are not similar. Here's one that has a whole bunch of things that are true. These two matrices, the identity matrix and the matrix 1, 1, 0, 1, they have the same determinant, 1. They have the same eigenvalues, 1. The algebraic multiplicity for 1 is 2 for both of them. The rank of both of them is 2, and they're both invertible. And yet these matrices are actually not similar to each other. To know why they're not similar is easily figured out because one of them is similar to a certain type of matrix called diagonal matrices, while the second one, 1, 1, 0, 1, is actually not similar to diagonal matrices. So therefore, they can't be similar to each other. What can we use then? How can we use that theorem? It's actually really useful to show that two matrices are actually not similar. So look at these two matrices. These two matrices have different determinants. So then instantly they can't be similar because similar matrices have the same determinant. These two matrices actually do have the same determinant, but they don't have the same rank. One's rank 2, one's rank 1. So then they can't be similar. Also, in the first matrix, it has an eigenvalue of 1 and its algebraic multiplicity is 2. But the eigenvalue 1 in the second matrix has only an algebraic multiplicity of 1. They have different algebraic multiplicities for that one eigenvalue. So they can't be similar. All right, and I think it's enough for that video. In the next video, then we'll talk about why we want similarity, at least for now.